Okay, we have depth versus time data for the water flowing out of the bottle. Okay, depths here, and hypothetical clock times here. These aren't realistic. This 300 especially is just completely off the wall, but I just wrote the numbers down. And we can, from each line of the equation, we get, from each observation, each time and observation for each depth, we get an equation, okay, by substituting the y value for y in the form y equals at squared plus bt plus c, substituting the t value. Okay, now this is from the MCR class, and people were very adept at doing this. They had no trouble writing out the equations. Okay, so then this equation translates to this equation. All we do is square the 10 to get 100A, 10B, C, reverse the sides, we get this equation. We do the same thing for every line. I ask people to write out every line here, and I would suggest that as an exercise if you're not clear on this. And then write out the corresponding equation with the sides switched and the numbers worked out. Okay? So we get, anyhow, you can verify it, we get these 5 equations. We then picked these 3 equations and we solved for the values of A, B, and C. Now we're going to go through that process, but just to see, we solved for the values of A, B, and C, and we got A equals 67/600, B equals negative 177 over 20, and C equals 1316 over 6. Okay, this is what we got. Now, a lot of this is based on arithmetic that I did in my head, so I'm pretty sure about this one and this one. I feel reasonably sure about this one too. Okay, that then gives us the values of A, B, and C to put into this form to obtain an equation for y as a function of t, so that we could, given a value of t like 72, we could plug in 72 for t, plug it into this function, and get a value of y. Now, this is based on real-world data. There are all kinds of uncertainties in the data. In the first place, the time was just measured to the nearest count. Okay? There was hopefully a steady count. Time was measured to the nearest count. Well, that means the real time between these depths was actually some fraction. It wouldn't have fallen right exactly on the count. Okay, as a matter of fact, I asked people to write down the last count they heard. So almost all of these counts are a little bit short, because the last count they heard, there's been some time between when they heard that and when they saw the signal to write down the time, but the next count hadn't yet been made. So we could be off by any fraction of a count on all these numbers, and we would always be a little bit short. That's worth considering. It's worth understanding and worth considering what that does to our model. Okay? Well, anyhow, if we put a t in, we would get a prediction of the time, of the depth, so we would know about when that depth would be expected to occur. Now, we did write down a decimal approximation. Because of the uncertainty in measuring the time, it makes no sense to be really completely meticulous about the fractions and get exact results when we don't have exact data. Well, for the relative uncertainty in this data, since we could easily be off by, say, 1 count out of 100, 1%, it would make sense to just use 2 or 3 significant figures, and I'm not going to talk a lot about that. Hopefully you've got some awareness of significant figures. Each of these numbers is then rounded to 3 significant figures. Okay? Now, another thing before we move over and look at the solution of these 3 equations, we didn't solve these 3 equations. Okay? But it's likely that these 3 equations, matter of fact, it's certain because of that silly number 300 there, that these 3 equations are going to give you something at least a little bit different that these equations get. So you would get different values of A, B, and C. And of course, with the 300 in there, you get very different values of A, B, and C. But even with good data, with the data that people actually took, we're likely to be at least a little bit off. In other words, there's uncertainty in all of this data. We're not going to get exactly the same values of A, B, and C, but if the quadratic model is really the right model for this phenomenon, we're going to get reasonably close values if we have good data, okay? So, well, next we're going to go on and solve this system of equations. We're not going to solve this one. We're just going to solve these first three as examples, and then, of course, people are asked to solve three equations for each of their trials, okay, for each of their sets of observations. And we'll see how that works out when we get there.